Hi, everyone, and welcome to our fourth lecture of CSC 110. In this lecture, I'm going to continue with our work on binary numbers and extend that into arithmetic, binary arithmetic. Okay, and just to remind you why we are studying binary numbers, let me just go over the points I made last time, and then we'll get into binary arithmetic. The first point, I guess, is that binary numbers, that is representing numbers or representing all of information as a sequence of ones and zeros, is actually the essence of the digital age or digital technology or digitization, okay, or the information age, as you might call it. And computer technology is changing all the time. Phones are getting better, tablets are getting better, new devices are being created that you may not even know about yet, and they'll eventually make it down to the public. And I don't want to just teach you, the specifics of any one of them, because they'll be gone in a few years and there'll be something better in its place. But there's something that's not going to change, and it hasn't changed since computers really came into our world at the end of World War II, and that is their underlying functioning, and that is the what I call the essence. Like, what is it? What is a computer? Okay, and to understand that properly, you have to understand binary numbers. Okay, so that's the first reason. You might say it's a bit theoretical. You might say, can I live life without this? Yeah, but you wouldn't be as well educated if you didn't understand it, especially since it's the fundamental technology that we use today. Okay. The second thing is that along the same lines, I kind of want to really give you an idea of how you can build a mechanical mind, okay? And that's what CGP Grey called it in his video. So, mechanical muscles are a little bit easier to picture, but what would be a mechanical mind? Like, how would you build a machine that does things that the human mind does, okay? So I'm not going to do all of that because that would be way beyond the scope of this course and probably beyond the scope of even computer technology today to be able to do everything the human mind does. I don't even know if that would ever be possible. Okay, but at least I can do this much. I can build for you an adding machine. Okay, and this is going to be a device which is made out of switches. And remember, switches are like, they're either in the on or off position. That's either a 0 or 1. There's your binary. Okay, and so what I'm going to do is I'm going to build a device out of switches such that it adds. Okay, now I won't actually physically build it, although you could. I will design it using computer software that is used to design other computer hardware. Okay, so we'll take a look at that when the time comes. All right, and the next thing is, and this is now getting a little bit more practical, all human information can be represented as binary. Okay, so right now I'm just doing numbers. And actually, I'm only doing whole numbers, okay? I'm not even doing fractions and things like that. But numbers can be represented as binary. The other thing that can be represented as binary are letters, like letters in the English alphabet. All alphabets, not just English, but all alphabets, including, the various kinds of, like, symbols that they use, like, like in Spanish you have the tilde over the n and things like that, or accent marks. Okay, but even alphabets that are or writing systems that are not even alphabet based, like Chinese and so on, all of that could be represented as a sequence of ones and zeros. And you might say, well, how does that work? And color can be represented as a sequence of ones and zeros, in other words, as binary. Pictures can be represented as binary. Audio can be represented as binary. Video can be represented as binary. X-rays can be represented as binary. Ultrasound, okay, and other kinds of diagnostic information can be represented in binary. And at this point, you're starting to see that, yeah, maybe this is going to impinge on your life, especially if you're in the medical field, because what does it mean to have, all of your diagnostic information in digital form? In other words, represented as binary. Okay, and finally, probably the most practical thing that'll come out of all of this is that we can now measure information precisely. And what I mean by that is, like, if you wanted to measure, I don't know, the edge of this table, or say the size of your monitor or whatever, you would get a ruler and you'd put the ruler up against your monitor and you'd be able to measure how big it is. Okay, and depending on how good your ruler is, you can get a pretty good measurement. All right, so you can measure things like the lengths of things. Okay, you can measure things like time using a clock. You can measure things like the amount of stuff there is, the amount of substance, that's the weight, or more properly, the mass. Okay, those are the kinds of things that you study in chemistry and physics, and in biology too. Okay, in all of the hard sciences. But there's one other thing you can measure now, and that is information. Okay, so you can actually measure information, and when you buy like a USB drive, okay, like the USB sticks that you plug into your computer, or you buy a new laptop, and you say, how big is the disk? How big is the memory? Not the volatile memory, not the RAM, but the disk where you can store stuff, and that'll be given to you in like a number like 64 gigabytes or megabytes or terabytes and things like that. And so that gigabytes here, that's an exact measurement. Okay, there's an exact value associated with that, and you wouldn't be able to understand measurements of information if you didn't understand all of the binary leading up to it. Okay, and so what I'm hoping to do out of all of this is not only educate you as to the kind of technology that is changing our world today, but also give you some practical information so that as you go forward into the future and new technologies, new computer technologies arise, you'll have an appreciation for what they're doing, and you won't be like totally clueless about them. Okay, and so it is worth going through this. It might seem like binary numbers are not my thing, this is not my major, but to be a well-educated person living in the digital age, I think some of this is important. The course progressively becomes more practical as we go on anyhow. Okay, so let's continue. All right, before I jump in and actually show you how to do binary arithmetic, let me quickly remind you about how numbers have been represented in the past. The first way that numbers were represented was what you might call very early numerals. Okay, and basically each line, each stick, as I have here in quotes, each stick represents an object. So if you had 3 cows, you'd draw 3 sticks. If you had, I don't know, 5 houses, you would draw 5 sticks. Okay, and stuff like that. Now, that system is pretty good. I mean, it's getting there. It's hard to represent large numbers that way because you'd have lots of sticks. So maybe under 10 you'd be okay, but if you try to get up to 100, I mean, would you be able to tell the difference between 100 sticks and 101 sticks? Not very easily, right? And so it's hard to represent large numbers, but it's easy to do arithmetic because if you have 2 sticks and you add 3 sticks to it, you'll have 5 sticks. Okay, so the arithmetic is kind of obvious that way. All right, though I shouldn't say arithmetic, addition at least. Okay, but multiplication and those other things, they get a little bit harder, but they're still easier in that than they are with Roman numerals, which is the first way of representing numbers that we had in the West. Okay, so I mean, the Greeks had a way of doing it, the Babylonians had a way of doing it, so I shouldn't be unfair, but I don't want to go through every single ancient number system. The one that most people are still familiar with today are Roman numerals, and the way Roman numerals worked is they had a symbol for 1, 5, 10, 50, 100, and so on. Okay, so they had units of ones and multiples of them, and fives and multiples of them. And I won't go how you put together a Roman numeral, but you could certainly write down Roman numerals this way, and you could write down even very large numbers. Okay, so you could easily write down, like usually you'll see dates on the side of buildings, and it'll be like this building was built in 1998. And it won't say 1998. It'll actually have the Roman numeral equivalent of it. Okay, so it's not too hard to write large numbers this way, but try to do arithmetic with Roman numerals. Even just adding is a real pain because there's no natural rules by which you combine the symbols. Okay, and so that was a limitation. So the next writing system that was adopted were Arabic numerals. They're so called because they came to us from the Arabic world, but they might have actually originated in India. I don't know the history, and I don't want to say more. You can look that up on Wikipedia if you're really interested in that history. But they came into Europe, around the year 976, I think. Is the first evidence that we saw of Roman numerals, and the way they work. They're the numbers we use today. Okay. So with the decimal system, there are 10 unique symbols. Okay, that's like 0 through 9. There are 10 unique symbols. Okay, but you can extend Arabic numerals from a decimal system that is base 10 with 10 unique symbols to octal with base 8 with 8 unique symbols, or hexadecimal with 16 unique symbols. We won't study those, but we will study binary. Okay, so these are still Arabic numerals, but they're Arabic numerals with just 2 unique symbols, and the 2 unique symbols are 0 and 1. Okay, if you do that, then the columns represent powers of the base. So for instance, for decimal, you would have the ones column, then followed by the tens, the hundreds, the thousands, and so on. Be careful, I wrote here from left to right, but when we write the number, those columns, the rightmost column is the ones column, the next column over to the left is the tens, the next column over to the left is the hundreds, and so on. Okay, and so the columns increase by a power of 10 as you go from right to left. Okay, but you know that, but I just want to be very clear. Okay, the same thing for binary, but with binary you only have two symbols, so you have a cycle of 2 before you bump up the next column, and so the columns go as powers of 2. The first one is the 1s, then the 2s, the 4s, the 8s, 16, 32, 64, 128, and so on. Okay, and again, the rightmost column is the 1s column, the next one to the left is the 2s column, the next one to the left is the 4s column, and so on. Okay, so that's how Arabic numerals work, and they were originally for decimal because we have 10 fingers, right? And but now we can extend that to base 2, and we are. Okay, now what was great about Arabic numerals? Well, they're easy to count to large numbers, okay, as you know, and they're also easy to do arithmetic with. So now you have things that are easy both ways. So you could do addition very easily with Arabic numerals, and I'm going to actually go through that in this video. That's exactly what I'm going to go through, and also multiplication and the other arithmetic operations. The four major arithmetic operations are addition, subtraction, multiplication, and division. Okay, and here's what's even going to be more amazing. It's easy in decimal, as you know, because that's a lot of the arithmetic that you learn in grammar school. Okay, but it's even easier in binary than in decimal, okay, to do arithmetic. And you might say, whoa, I mean, binary is so weird. It's only weird because you're not familiar with it. But if you get familiar with it and you have to do addition in binary, or you have to do multiplication in binary, or you have to do even long division in binary, you're going to be amazed that it's easy in binary, whereas in decimal it's kind of hard. So why did computers go with a binary system for its machinery, for its underlying machinery, rather than a decimal system? There's two reasons for that. The first reason is it's easier to make a switch which is either on or off. Okay, so that's binary. If you wanted to make a switch which had 10 different positions, that's a little harder. Okay, so one thing is just the physical hardware is easier on off, okay, for binary, and the other reason is the algorithm is easier. Okay, in other words, the algorithm means just a step-by-step procedure by which you would do addition in binary. That's easier if you want to add in binary than it is in decimal. Okay, and so there it is. In this lecture, I'm going to teach you and expect you to know how to do binary addition and binary multiplication. Okay, you're also going to see binary subtraction and binary long division. I'm not going to expect you to be able to do subtraction or long division. The reason I'm going to show it to you is because long division with decimal is really hard. So I'm going to show you how hard long division is in decimal, and then when we get to binary long division, you're going to go, oh, that's trivial. Okay, there's none of the kind of guesswork that you need in decimal when you do long division. In binary, it either divides in or it doesn't, 0 or 1. And so it's very easy. You just could divide very, very quickly without much thought. And that's kind of the point. If you say without much thought, that really means a simple algorithm. And the simpler the algorithm, the easier it is to build a machine that does that algorithm. Okay, so let's start with addition here. Okay, so before we start adding in binary, let me just remind you how you add in decimal. Okay, so I guess I'm going back to maybe grade 3, grade 2, I don't know, some point like that. And you remember you had a question like add 37 to 485. Okay, so you say, well, how do I add those two? And they would ask the question exactly like this. Okay, they would ask the question like that. And the first thing you would have to do is what? Line up the columns. Okay, line up the columns. And so here I'm lining up the columns like that. All right, now what you're seeing there on the first row is the hundreds, tens, and ones. That's not part of the addition. You don't have to put that in there. I put that in there just to remind you what those columns mean. Okay, so what those columns mean. Okay, so the rightmost column here, that's the ones column. The next one to the left is the tens, and then the hundreds, and if there were more columns, 1,000, 10,000, and so on. Okay, remember this is decimal now, okay, not binary, so they go up by factors of 10. The next column is 10 times the previous column. Okay, great. So you've got them lined up. So you see 37, that 7 is in the ones column, so there's the 7 in the ones column. And that 485, the 5 is in the ones column, and there it is. There's the 5 in the ones column right there. Okay, and then of course the 3 is in the tens, and the 8 is in the tens, and the 4 is all by itself in the hundreds column. Okay, now what? Well, what you can think about now is like you can imagine maybe working with money. Okay, so the way you could understand this is that 37, if you were representing this in terms of ones and $1 bills, $10 bills, $100 bills, and so on, a 37 is like 7 ones and 3 tens. Okay, so if you said, look, I got to give you $37, you would give out 7 ones and then 3 tens, and you'd be done. Okay. Similarly, if I had to give you $485, it would be I would give you 5 ones. Okay, but we're not done yet. Then I would give you 8 tens, and then we're not done yet. And then I would give you 4 $100 bills, and now we're done. Okay, I've given you 485. Okay, and so when you put these two numbers together like that, you could say, well, look, the 7 and the 5 there, this 7 here, and this 5, they're in the ones column. So that's like I have 7 ones from this one, and 5 more ones from that one, for a total of 7.7 plus 5 ones. Okay, so do you see how I did that? I had 7 ones from the first pile and 5 ones from the second pile. So now altogether I have 7 plus 5 ones. Okay, same thing with the tens. I would have 3 tens from 37 and 8 tens from 485, and so altogether I would have 3 plus 8 $10 bills. Okay, and then finally I would have that 4 $100 bills, because that's all by itself. Okay, so that's what I would give you. Like if I had to give you $37 and I gave you them as 7 ones and 3 tens, and then I had to give you an additional 485, and I gave you that as 5 ones, 8 tens, and 4 100s, and you put the piles together, you would discover that you have 7 plus 5 ones, 3 plus 8 tens, and you would have 4 $100 bills. Okay, well, we're not done adding, because the next thing is you realize that 7 plus 5 ones, that's like 12 ones. Okay, but you could take 12 ones and you could say, you know what, I'm going to replace those 12 ones with 2 ones and a 10. Okay, so because I went over 10, I'm going to say, look, I'm going to take away these 12 ones and I'm going to replace them with 2 ones and a 10, for still a total of 12. Okay, and so the 7 plus 5 ones can be replaced with 2 ones and a 10, and then just recollecting the terms, I have 2 ones and I have 1 10 from here. Okay, but then I also have 3 8s and a 10, and that would give me a total of 1 plus 3 plus 8 tens. Okay, all right, so now just did a regrouping. Now we say, okay, let's look at the tens column. So 1 plus 3 plus 8 tens, that's like 12 tens. Once again, I could say, well, 12 tens, that's like 2 tens and 100. Okay, and so I'm going to take those 12 tens and I'm going to replace them with 2 $10 bills and a $100 bill. And now my addition looks like this. This is from before. We have 2 ones, but now we have 2 tens and a $100 bill. That was the 12 tens from before, replaced by 2 tens and a 100. And then I'm just going to regroup these, and it turns out that I have 2 tens and I have 1 100 from the regrouping of the tens, plus the 4 100s originally, so I have 4 plus 1 100s. And then finally, I'm down to the answer as 2 ones, 2 tens, and whoops, I lost my 5. There we go. And 5 $100 bills. Okay, now if you take a look at those steps, I hope that wasn't too confusing. I really went very carefully. You'll notice this step here, I put 2 asterisks there. That was the regrouping, where I had 12 ones and I replaced them with 2 ones and a 10. And then over here, I also had these 2 asterisks. I had another regrouping where I took the 12 tens and replaced them with 2 tens and a 100. Okay, and then I regrouped everything together and I got my final answer. Those regroupings are basically carries. Okay, and so now that explains why the way we add works, where you add a column and then you put the least significant figure in the below the line, and then you put the carry into the next line. Okay, and what I mean by the least significant and the carry, that'll be obvious in the next one. Okay, so basically the carrying occurs when you have, because in decimal the carrying occurs because you might have a single digit like a 7 here and another single digit like a 5, but when you combine those 2 single digits, you're going to get a double digit like 12. Okay, that's 2 digits, 1 and a 2. Single digit means you just have one symbol, 7. And another single digit, 5, it's just one symbol, 5. But when you add 7 and 5, you get two symbols, a 1 and a 2, okay, in Arabic numerals, and that's a double digit, okay? And so because you get this double digit, you have to put the least significant figure, that 2, below the line, because that's part of the column that you're in. But the next one over, the carry, this one has to go over into the next column because it's a regrouping. Okay, whenever you have a regrouping of 10 ones, you get a 10, and that's why it goes into the tens column. Okay, I hope that was clear. All right, I'm trying to really nail down why the way we add with the carries works. Okay, and so over here, ignore this line just for a second. That's there because those are the carries actually. Just start in, how would you add? You would take 7, you would start in the ones column, you would take 7 plus 5, and you say, what's 7 plus 5? Well, 7 plus 5 is 12, but you wouldn't write 12 down there. That's not what you do, okay? What you'd write is the 2 down there, which is the least significant figure. That's the smaller of the 2 columns, okay? You put the 2 down there, and the 10 part of the 12, okay, this part here, you put into as a carry into the next column, okay? Because it belongs in the tens column. All right, so there you go. So once again, 7 plus 5 is 12, or we would say 7 plus 5 is 2, carry 1. Okay, now you're ready to add into the tens column, and what do? You go 1 plus 3 plus 8 is 12 again, but 12 we think of as 2, carry 1, like that. Okay, and then finally you go, okay, 1 plus, that's a 0, so any blanks to the left are 0. Okay, so 1 plus 0 plus 4 is 5, and there you have your answer. Okay, so very quickly, 7 plus 5 is 2, carry 1. 1 plus 3 plus 8 is 2, carry 1. 1 plus 4 is 5, and you have your answer. All right, so before we move on to binary, because I'm going to do the exact same thing in binary, what did you need to know to do this right? Well, the first thing is you needed to know how to add two single digits. Okay, so like a 3 and a 7, or a 5 and a 2, or 9 and a 1, or 9 and a 7. Okay, so one single decimal digit plus another single decimal digit. Okay, so you need to know how to do that. And the other thing you need to know how to do is how to carry. Okay, well, the carrying part is kind of easy. It's this part. I wouldn't say it's hard, but you got to memorize a table. Okay, you got to memorize an entire addition table. Now, usually we're used to like memorizing our multiplication tables, okay, because addition tables are a little bit easier to reconstruct on the fly. But there is an addition table, and here's what it looks like. So this row right here, that represents, whoops, I went too far. Okay, there you go. That row right there that I have highlighted, that represents, say, the first number in your addition. Okay, and this column over here, all right, this column over here, that represents your second number. Okay, oh, something wrapped wrong here. Okay, hold on, let me fix this. Answer there. It's still not. Okay, that's better. Sorry, I had a bit of a wrap problem. Okay, the thing was wrapping. Okay, so once again, this first row here, that is the first number in your addition. This column here, like that, that is the second number in your addition. And the stuff that's in here, that's your answer. Okay, so for instance, if you wanted to do 4 plus 3. Okay, so you did 4 plus 3. You say, what's 4 plus 3? I know it's 7, it's obvious, but how would you get it out of this table? You would go, well, 4, my first number is 4. My second number is 3, right here like that. Whoops, 3 like that. So you had 4 and 3. And then you would just cross-reference, okay? So you would go all the way over to here, and there you go. That 7 is in the column headed by 4, and in the row that begins with 3, and so 4 plus 3 is equal to 7. Okay, and so you need this table. Now, I didn't even fill out the whole table because it wouldn't fit in my word processor, but on the top here you would have to go from 1 to 9. Actually, technically you'd have to go from 0 to 9. Okay, so you'd need 10 symbols across the top, cross-referenced with 10 symbols in this column here like that. And so you'd have 10 by 10. You'd have a table which is 10 by 10. 10 by 10 is 100 entries. Okay, so if you want to add, you have to be able to add single digits to single digits. Okay, and to do that, you have to have a table which is of size 100. Okay, and you say, well, why do I have to add single digits to single digits? Well, just remember here, whenever you're adding, you're always adding, like, there's a single digit 7 and you're adding it to another single digit 5. Okay, here you're also adding single digits, but you're not even adding 2 single digits, you're adding 3, okay, digits, like 1 plus 3 plus 8. But whenever you have, like, additions of 3 or more numbers, you can always break them down into additions of a pair at a time. Okay, this is known as association and addition. Okay, so you could do 1 plus 3 first, and that gives you 4, and then you could do 4 plus 8, and that gives you the 12. Okay, still, you have to go single digit by single digit. Okay, all right, so there you go. That's how you add. I'm going to do one more just to quickly remind you how this works. Okay, and so you would start off 9 plus 2. Okay, so I better tell you what the question is. So the question is, add 7,489 to 572. Okay, so you're just given this question, probably, like, I'm going to guess grade 3 or so. And what you would do is you would line them up. Here they are lined up. Okay, there's the first number, and there's the second number. Okay, lined up. And then you would start in the ones column. You go 9 plus 2 is 11. So that's 1, carry 1. Okay, and then you go 1 plus 8 plus 7 is 16, and you go, that's 6, carry 1. And then you go 1 plus 4 plus 5 is 10, that's 0, carry 1. And then you would go 1 plus 7, and that's nothing there, like that, is 8. And there's your answer. Okay, and notice that in doing that, I had to make lookups in the table. Like, I had to look up for the very first column here, I had to look up 9 plus 2 is equal to 11. Okay, now, like I said, you probably have this memorized because addition is really easy. Okay, and so 9 plus 2, even if you didn't have the table, you could easily, just say, oh, I have 9 fingers and add 2 more. I went over 10, or I went 1 over 10, so I have 11. Something like that. Okay, all right. Nonetheless, this is not an easy algorithm for a machine to emulate. Okay, so if you wanted to build a machine that operated like this, you'd say, how in the world would I do that? How would I build a machine that does basically what I just did here? Okay, and not just for particular numbers, for any numbers, because I could put any number for the first one and any number for the second one, and then I would use my machine, and then magic would happen, and out would come my answer. Well, they did have machines like that. In fact, the first person to think about using gears to make machines like that was a fellow named Babbage, and he built the first computer, if you want to call it that, in the 1800s. All right, and as you can imagine, it was like a room full of gears, and gears turning other gears, and it was kind of a crazy machine. Okay, and he kept designing it bigger and bigger and bigger, and he could never really complete it because the number of gears that you would require would be more and more and more. But at least for addition, these machines were used by the public. They were the mechanical cash registers. And so if you just Google for, like, mechanical cash registers internals, okay, I put the word internal there so you could see inside, otherwise you just get the picture of the externals. You would see things like this. Okay, so this is a cash register from many years ago. I think this one's from 1957, and you could see that you had some buttons to enter in the value, like how much money you were going to how much money each item was. And then on the side here that you can't see, the side that's facing away from us, there was a crank, and you would crank it, and that would then add in the next number, and it would add in the next number, and it would add in the next number, and so you'd have a total. And if you had 3 items that were like the same amount, you would crank it 3 times. And if you had 5 items that were the same amount, you'd crank it 5 times, and it would just keep adding in the same amount, adding in the same amount, and just keep a running total. Okay, now internally, what this had was this. It basically was just made up of all these gears inside. I couldn't really get a very good picture, but you had all these gears turning other gears turning other gears. And so, yeah, it was possible to make a machine that did this, but it's not as easy as with binary. Okay, and so let's now start to do this algorithm in binary. So here I say, let's translate this into binary. What I mean by translate this, I mean let's do the exact same thing that we just did for decimal numbers. Let's do it for binary. Okay, so remember, we needed 2 things. The first thing we needed was that addition table, and the other thing is we needed to know how to carry. Okay, so and then we could add any size binary number to any other size binary number. Okay, so first of all, there's the addition table in binary. It's trivial. Now, why is it trivial? Because there's only 2 possibilities. Remember, this is single digits. We're not adding big numbers here. We just have one single digit for our first number and a single digit for our second number. So the first digit is either a 0 or 1. So there's only two possibilities. The second digit, which would be this column here, is either a 0 or a 1. Okay, and so there's only four possibilities, and there it is. This is your addition table. Okay, now the way you would read it is you'd say, look, if I was going to do 1 plus 0, I would do 1 for my first number plus 0 for my second number. So 1 plus 0 is 1. Okay, or if I wanted to do 1 plus 1, I go 1 plus 1, and then I cross-reference it in my table, and I go 1 plus 1 is 10. Okay, you're tempted to say 2. 1 plus 1 is equal to 2 in decimal, but in binary, 1 plus 1 is equal to 1, 0. Okay, 1, 0. So you could write it as a table like that, but because it's so short, you could just write it out. You could just write out the four possibilities. What are they? Let's go through them. One possibility is 0 plus 0. Well, if you've got nothing and you add nothing to it, doesn't matter whether it's decimal or not, you still have nothing. Okay, so nothing plus nothing is nothing, or 0 plus 0 is 0. 0 plus 1 is 1. Okay, is that obvious? Well, let me do it in two hands. Okay, so one hand is going to be 0 and the other hand is going to be 1. Okay, so here's my 0, here's my 1. How many fingers do I have putting them together? 1. Okay, so 0 plus 1 is 1. 1 plus 0 is 1, and then finally 1 plus 1 is 1, 0. Okay, and that one in my fingers. Okay, so my hands, sorry, so there's 1 and there's another 1, and I put them together, and now I have decimal 2 but binary 10. Okay, 10 like that. All right, so there is a carry. Like if I'm in a situation where I have to do 1 plus 1, I would have 0 carry 1 like that. All right, and so you'd have to carry, but it's still, the rest of it still works the way it does in decimal. Okay, so now we can start with our first addition. Okay, our first binary addition. And remember, I'm going to build a machine that does this. Okay, so right now you're using your brain, and I'm going to build a machine that does that. And what is that machine? It's a mechanical mind. Okay, so like with the mechanical muscles, they were an externalization of a human function. What do I mean by that? The bellows is like our lungs, but our lungs are us, and our bellows are something that works like us and does the same thing as our lungs do, so we can blow. Okay, and like a lever, we didn't talk about levers, but those are like mechanical arms. Okay, so rather than lifting with your arm, you lift with the lever. This is a mechanical mind. Rather than adding with your mind, you'd be adding with this machine. That's what a computer is. Okay, if you get that, you essentially understand what computer technology is all about. Okay, so let's go on here. Okay, now I've got 3 rows here. Ignore this top row. That's there because it's the carries. Okay, but we're just going to add 1011 to 101. What's the first step? We'll just concentrate on these two lines here like that. The first step is to align them. Okay, in the ones column, the twos column, the 4 and the 8s column. Okay, so this number here, 1011. Here's the ones, the twos, the 4s, and the 8s. Okay. And this one, 101, there's the ones column, twos column, and 4s column lined up. Okay, so now what we're going to do is we're going to go 1 plus 1. That's the first step in this addition, because you always start with the ones column in decimal or in binary. So you go 1 plus 1. Okay, and you say, what is 1 plus 1 equal to? Well, you could just look it up in the table here like that. 1 plus 1 is equal to 10. Okay, now don't think of it as 10. Think of it as 0 carry 1. Okay, because before, let me just remind you what happened here. When I did, we could do it in this one. When I did 9 plus 2, okay, I didn't say, the answer is 11, but I said it is equal to 1 carry 1. Or maybe a better example is up here when I did 7 plus 5. 7 plus 5 is 12. But I didn't just say 12, I said 7 plus 5 is 2, which you write below the line in the ones column. Carry 1, because you have to put that 1 into the tens column where it belongs. Okay, same thing here in binary. So I'm going to go 1 plus 1 is 10, but I'm going to say 1 plus 1 is 0 carry 1, because that 1 belongs in the twos column. Okay, we're good so far? All right, so 1 plus 1 is 0 carry 1, and get used to saying it that way. All right, now what? Now I've got 1 plus 1 plus 0. Well, the 0 doesn't add anything, so it's like 1 plus 1 again. Okay, and 1 plus 1 is 0, carry 1. Okay, 1 plus 1 is 0, carry 1. And then I am in the third column here. This is the fourth column, like that. And I'm going to go 1 plus 0 plus 1. Well, you could just drop the 0 because it doesn't change anything. So I still have 1 plus 1. And 1 plus 1 is 0, carry 1. Okay, remember this column is the carries column. So 1 plus 0 plus 1 is 0, carry 1. And then finally, I'm in the eighth column, and I'm going to go 1 plus 1. And that space there, that's a like leading 0. Okay, so 1 plus 1 is 0, carry 1. And we're done with the addition. All right. Now, we're going to practice more of these. So if you missed a little bit of the details there, you can either rewind the video or else just wait till I move forward and we'll do more of these. Okay. So there you go. We basically added two binary numbers. And this one had a lot of carries, and you'll discover that. With binary numbers, you're going to get a lot of carries, okay? But nonetheless, we have the answer. And the answer is, if you take 1011 and you add 101, you're going to get 10000 like that. Okay, so there you go. There's the answer. All right. Now, we could stop and say, fine, we're done. But since we're practicing binary numbers, remember last lecture, I taught you how to convert binary numbers to decimal. It doesn't matter whether you add in binary or you add in decimal. You should still get the same answer both ways, okay? And so if you convert the binary numbers to decimal numbers and then add them in decimal, it should work out, okay? It should work out. So that's what I did over here, and I'm going to do that for a few examples. Why am I going to do that? It's practice, and it shows you that it does work. Everything checks out. So the first number that we are going to add is 1011. 1011. Okay, so remember how you convert this? You start from this side here, okay, from the rightmost side, the ones column, and you go, I have a 1. Great, so you put a 1 there. And then you go to the next column. You have a 2. There's a 1 in the 2's column, so you have a 2. There's nothing in the 4's column, so skip 4. I have a 1 in the 8's column, and so you add an 8. Okay, so I have a 1, a 2, and an 8. So 1 plus 2 plus 8 is equal to 11. Okay, that's equal to 11. The next number is 1, skip 2, and 4. Okay, so it's 1 plus 4, which is equal to 5. So your top number is decimal 11. Your bottom number is decimal 5. 11 plus 5 is 16. Did it work out? We'll take a look here at the answer. That's the ones column. You have no 1s. You have no 2s. You have no 4s. You have no 8s. And that one is in the 16s column, and so you have just 116, okay? And so it works out because top number is 11, second number is 5, you expect the answer to be 16, and 10000 is 16 in binary. So it worked out, okay? All right, now before I move on, I pulled a fast one on you, okay? And so there's something fishy there. You'll notice that in the ones column, I only added 2 binary digits. By the way, a binary digit is known as a bit. Okay, we're going to start using that word more often. Usually when you say a digit, what do you think of? You think of like a single symbol in decimal numbers, like a 0, 1, a 2, a 3, or 4. So if I have like 5, that's a digit. 7 is a digit, okay? If I had 37, that would be a 2-digit number. In binary, we don't call them digits because that confuses it with the decimal system, okay? We call them bits, okay? So each digit in binary is known as a bit, okay? So you'll start hearing me say that more and more often, okay? So when I added the first column here, I did 1 plus 1, like that, okay? Basically, I was just adding 2 bits, all right? And I got 1 plus 1 is equal to 10, okay, which I said out loud as 0 carry 1 because it was part of an addition. But when I got into the next column, I actually added 3 bits, okay? So I had 1, which was the carry from the previous one, plus 1 plus 0, okay? So you say, well, you were able to do it because, 1 plus 1, you could ignore the 0. 1 plus 1 is equal to 0 carry 1. But technically speaking, I have that 0 there. So what I'm really adding in the 2's column here is 1 plus 0. Okay, so in the 2's column, I was actually adding 1 plus 1 plus 0. Okay. Again, you say, well, you could just drop the 0. I know, but there's going to be some situations where you can't, and you'll see why in a minute. 1 plus 1 plus 0 is the same as 1 plus 1, which is 1, 0. Again, I would say 0 carry 1. In the 4's column, I had a similar situation where I had a 1 from the 2's column being carried over from the 2's column plus 0 plus 1. Okay, and so if I take a look at the 4's column, I had 1 plus 0 plus 1. I'm still adding 3 bits. One of them happens to be a 0, which I can drop. So 1 plus 0 plus 1 is the same as 1 plus 1, which is 1, 0, or 0 carry 1. Okay, and then finally in the 8's column, I had the same thing again. Okay, and I got my answer. But, so in the 8's column here, like I said, I got the same thing again. Okay, but you might wonder, is there ever going to be a situation where I might have 1 plus 1 plus 1? Because if you say 1 plus 1 plus 1, you go, well, what is that? If you take a look at the table here that I gave you, okay, you might say, well, I don't see where you can add 3 bits there. Basically here, you could just add the first number might be a bit, the second number might be a bit, okay? But where's the third number that is the third bit? It's not there, okay? So let's take a look at how we would do that. The only situation where you have to, increase that addition table is the situation where you're adding, where is it here? Oh, right here, sorry, went too far. 1 plus 1 plus 1. You can, in addition, get into the situation where you're adding 1 plus 1 plus 1. Okay, now I don't have 3 hands, but if you take 1 and then you add another 1, you get 2. Okay, or 1, 0. But then if you add another 1, you get decimal 3, and decimal 3 in binary is 1, 1. Okay, so you might get into a situation where you're adding 1 plus 1 plus 1, and the answer is 1, 1, which, as we're doing this addition, we're going to say that is equal to 1 carry 1. Why are we saying 1 carry 1? Well, because that 1 you write below the line, and the other 1 right here is your carry, which you write into the next column, which you bring into the next column. Okay, so 1 plus 1 plus 1 is equal to, in binary, 1, 1. Okay, 1 plus 1 plus 1 is equal to 1 carry 1. All right, so does that happen when you add, when you do addition in binary? Yeah, it happens quite often. There's a lot of carrying in binary. Okay, a lot more carrying in binary than there is in decimal. All right, so, but it's easier. The carry is easier because the carry can only be 1. All right, you're never going to carry a 0, because why would you carry a 0? Okay, so let's take a look here. So in my next question, I'm going to ask you to add 1, 1, 1, 1 binary to 1, 1. As you can imagine, there's going to be a lot of carries here. Okay, and so this is where you would start with this is where you would start like that. Okay, that would be the first thing. You would align the columns. Okay, and for this one, I did put that 0, that leading 0 in there. I could have left the space there, but I put that leading 0 in there just to show you that you're going to get into situations where you're adding 3 bits, okay, per column. All right, so let's go ahead and do this. Let me get rid of the spaces that I added there. Okay, and so let's start. We always start with the ones column, and so we say 1 plus 1. What's 1 plus 1? 1 plus 1 is 0 carry 1. Okay, so 1 plus 1 is 0 carry 1. All right, and then over here I'm going to go 1 plus 1 plus 1. What's 1 plus 1 plus 1? Well, that's the situation where you get decimal 3, or in binary, that's 1, 1. And so we will read that as 1 carry 1. Okay, and so over here, 1 plus 1 plus 1 is equal to 1 carry 1. Okay, and now we're in the 4's column, and we're going to go 1 plus 1 plus 1 is equal to 1 carry 1. Now we're in the 8's column, and here we're going to go 1 plus 1 plus 0. 1 plus 1 plus 0 is 0 carry 1, and we're done with the addition. Okay, so over here, by the way, these notes are also on Canvas if you want to look at them later. Just to summarize, take a look at what we did. When we were in the ones column, we started off with 1 plus 1 is 0 carry 1. Okay, so we did 1 plus 1 is 1, 0, and 0 carry 1. We write the 0 below the line, and we carry the 1 into the next column. Let me put a space in there so it's a little easier to see. Okay, so you write the 0 below the line because 1 plus 1 is 1, 0. So you write the 0 below the line and you carry the 1 into the next column. Okay, and then when we were in the next column, that's in the 2's column, we had the 1 that we carried and the 2 ones that were there from the numbers. So we go 1 plus 1 plus 1, and that gave us 1 carry 1. Okay, so in the 2's column we had 1 plus 1 plus 1, which is equal to 1, 1, and we say out loud 1 carry 1. We write 1 below the line and we carry a 1 into the next column. All right, and then in the next column we had the exact same situation in the 4's. 1 plus 1 plus 1 is 1 carry 1. Okay, so in the 4's column we had the exact same situation again. 1 plus 1 plus 1 is equal to 1, 1, or 1 carry 1. All right, and then finally in the 8's column we had 1 plus 1 plus 0, okay, which was 0 carry 1. Okay, so in the 8's column 1 plus 1 plus 0 is 1, 0, or 0 carry 1. So you write a 0 below the line and you carry the 1 into the next column, but there's nothing more in this next column, so that 1 is just there. All right, there you go. Okay, so that's basically addition in the binary system. All right, now once again you could say we're done. All right, we're done here, we don't have to go any further, but to check you might want to take those numbers and convert them into decimal and see if the addition works in decimal. Okay, so let's take a look here. My first number was 1111, and what's that in decimal? Well, there's a 1 in the 1's column, there's a 1 in the 2's column, so I have a 2. There's a 1 in the 4's column, so I have a 4. And there's a 1 in the 8's column, so I have an 8. Okay, and 1 plus 2 plus 4 plus 8 is 15. Okay, so 1111 is 15. Okay, by the way, we're converting this, but you remember you should have those numbers memorized. So you should just know from the chart that I gave you that 1111 is equal to 15. Okay, and you say, well, I might forget. Well, if you forget, okay, you could redo it. A 1 plus a 2 plus a 4 plus an 8 is 15. Okay, and what about 111? Okay, so we have a 1, a 2, and a 4. So if we add 1 plus 2 plus 4, that's equal to 7. Okay, so we're adding 15 and 7. Okay, and so the answer should turn out to be 22. Well, when we did it in binary, we got 10110 as the answer. So here it is. Okay, 10110 is the answer. So let's convert that to decimal. We have no 1s, we have a 2, a 4, and a 16. Okay, no 8s, there are no 8s, and a 16. So, okay, so we have a 2, there it is. We have a 4, there it is. And we have a 16, there it is. So 2 plus 4 plus 16 is equal to 22. Now, did that work? Well, the first number was 15. The second number was 7, and if you do 15 plus 7, you get 22. And so, ta-da, it works. Okay, so now you know how to add both in decimal, which you learned in grade 3, and you know how to add in binary. Okay, and it might look strange. Okay, I admit, the first time people see this, it looks very strange. But if you just follow the rules and try not to let your mind switch to decimal on you, because that's where it'll get you. I'll show you how to stop your mind from doing that in a second. But if you do it in binary, you add in binary, it's actually easier. There are less rules to memorize. Okay, you basically just have to memorize the 4 additions of single digits and then the other one, which is 1 plus 1 plus 1, and then you're done. Okay. The thing I think that at this point might seem very strange to you is because if you're going, I'm going to add 1 1 1 1 like that to 1 1 1, you're so tempted to think of that number in decimal, to think of it as 1111. No, don't do that. Okay, and don't even say that. Don't even read the binary number as 1111, because as soon as you do, you're thinking in terms of thousands, okay, hundreds, and so on, and you're in the decimal world. We're not in the decimal world here, we're in the binary world. And so you could hear that whenever I say a binary number out loud, I'll just read the digits from left to right. Okay, so I'll read 1 1 1 1 like that. Okay, or here's another one. Okay, how would I say that out loud? I won't try to even do it in decimal. I will just say the number is 101110 like that. Okay, so that's one way to stop your mind from going off into decimal. And the other way is you just have to force yourself, and when you see 1 plus 1, do not say 2. Okay, 1 plus 1 is equal to this many fingers, which in binary is represented as 1/0. Okay, so 1 plus 1 is equal to 1/0. Okay, and in the context of this addition, try to say it as 1 plus 1. 1 plus 1 is 0 carry 1. Okay, I don't have the carry up there, but up here. Okay, you go 1 plus 1 is 0 carry 1. And the other one is 1 plus 1 plus 1. So again, 1 plus 1 plus 1 is 1 carry 1. 1 plus 1 plus 1 is 1 carry 1. 1 plus 1 plus 0 is 0 carry 1, and so on. Okay, so just get yourself used to saying that, and you should be able to break the rules from decimal, interfering with the rules from binary. But like I said, once you realize what the rules are, once you've got that as a habit, it's trivial to do this in binary. Absolutely trivial. Okay, like I said, you basically have to memorize just these 4 additions up here. Okay, but because of the carry, you might get into the situation when you have 1 plus 1 plus 1, and then you just have to memorize one more. And what's that one more? You have to memorize this one. 1 plus 1 plus 1 is equal to 1, 1. Okay, so once you have these 4 rules like that, these 5 rules like that, you're basically done with knowing how to do addition in binary. Also, you have to know how to do the carries. Okay, let's just look back at the decimal here. For decimal, remember, to do it right, you would have to memorize 100 different answers. Okay, the answers are easy for your brain to come up with on the fly, but you'd have to memorize basically 100 different additions. You might say, well, 2 plus 1 is the same as 1 plus 2, so that reduces it from 100 to 55 different additions, but still, that's a lot to memorize. Okay, now in decimal, in binary, you're down to 4 plus this extra special case like that. Okay, so there you go. That's how you do addition in binary. Okay, so what now? Well, now let's just do it. We'll just practice. Okay, and I'll create a separate video that just does one problem after another. Okay, the reason I want to do it as a separate video is that some of you are going to go, this is obvious. I'm bored of watching all these videos where you're just adding one binary number after another, and multiplication too, because you'll be responsible for that. You see, I'm just bored of this. And that's actually a good sign, okay? Because if you're bored of doing it, it means you get it, okay? If you've done a whole bunch of these and you say, look, I just don't want to do anymore because I know what I'm doing. I always get the right answer. I'm bored of doing that. Then you got it, okay? So that's why I'm going to put practicing off in a separate video. But I do want to do a few more here just to make sure that everyone's got how it works, okay? So here's another example. I'm going to ask you to add 1 0 1 1 1 0 to 1 1 1 1 1 like that. Okay, so step number 1 is align them. So there's the first number and there's the second number. Now the first number had 1 2 3 4 5 6 bits. Okay, the second number has 1 2 3 4 5 bits like that, and so the top number is 6 bits, the bottom number is 5 bits long, and I just added the leading 0 there just so you could see that how the alignment worked. Okay, now what? Well, you start with the ones column and you do 1 plus 0. Sorry, 0 plus 1. I apologize. 0 plus 1. And you go, what's 0 plus 1 equal to? Well, 0 plus 1 is equal to 1. And there's no carry. If you want, you could put the carry in there. You could say, okay, 0 plus 1 is equal to 1 with 0 carries. Okay? And then you go, okay, well, now what do I do in the twos column? Well, in the twos column, you're going to go 0 plus 1 plus 1. 0 plus 1 plus 1, what's that equal to? Well, that's equal to 1 0. All right, and so that's the same as 0 carry 1. So over here, you're going to go 0 plus 1 plus 1 is equal to 0 carry 1. Okay, now you're in the fours column. And the fours column, what are you going to have? You're going to have 1 plus 1 plus 1. You're going to have 1 plus 1 plus 1. And that's equal to 1 carry 1. And so 1 plus 1 plus 1 is equal to 1 carry 1. And now you're in the eights column, and you're going to go 1 plus 1 plus 1, okay? And you're in the same situation again. That's equal to 1 carry 1. And now you're in the, let's see here, 1, 2, 4, 8. You're in the 16s column. And in the 16s column, you got 1 plus 0 plus 1, 1 plus 0 plus 1. 1 plus 0 plus 1 is 10. Okay, so 1 plus 0 plus 1 is 0, carry 1. And finally, you're in the 32s column, and you've got 1 plus 1 plus 0. And 1 plus 1 plus 0 is 0, carry 1. And so there it is. 1 plus 1 plus 0 is 0, carry 1. Okay, and we're done. All right. Just be careful of the usual things. I think you're probably good at, you understand this. So the least significant figure, that is the ones column, is to the right. It's the furthest to the right, and as you move over to the left, you go to higher and higher significant figures. So this is like the 2s column there, the 4s. Okay, although, so when you add, you start from the right and you go to the left. Although when we say the number out loud, we will always read from left to right. Okay, so here, this number, the top number here is 101110. Okay, but when we add it, we start with 0 1 1 1 0, and then we go to 1, like that. Okay, so just be careful about that. All right, I think you know that, but sometimes your mind might flip the direction in which you do things. Usually when you add, you know which way to go, but when you say the number out loud, you might think, well, you might accidentally say, the number is 0 1 1 1 0 1, only because that's the order in which you add the digits. But we don't do that. Okay, it's the same in decimal, so I don't know if you'll have that confusion, but it's happened to me a few times where I'll accidentally say the number out loud, and I'll read it from right to left rather than left to right, and the reason for that is precisely because that's the direction in which we read. Okay, all right, so next thing is you don't have to convert it to decimal, but let's do it because we're still practicing. On a test, I'll have questions for conversion, I'll have questions for addition. I won't mix the two, but since we're doing this together, let's do that. So the top number was 101110. Okay, and converting, that's in the ones column. There are no ones. There's a 2, there's a 4, there's an 8, there's no 16 and a 32. Okay, so no ones. There's a 2, there's a 4, there's an 8, no 16s, and there's a 32. Okay, add them all up, and you get that 2 plus 4 plus 8 plus 32 is 46. Okay, so also, even when we convert it, like a few times you saw me go left to right, but it's probably best when you're converting, especially when it's a larger number, to start with the right and then go to the left. Okay, so over here we'll do the same thing. We have a 1, we have a 2, we have a 4, we have an 8, and we have a 16. So 1 plus 2 plus 4 plus 8 plus 16, that's 31. Okay, now if you take 46 and you add it to 31, we get 77, and let's see if that worked out. So over here in our answer, we have a 1, we have no 2s, we have a 4, an 8, no 16s, no 32s, and a 64. Okay, so let's go through that again. We have a 1, no 2s, we have a 4, there's our 4, we have an 8, there's our 8, we have no 16, no 32s, and we have a 64, there's our 64. And if you do 1 plus 4 plus 8 plus 64, that's equal to 77. Okay, and that's what we expected, so it works. Okay, and I said they're magic, but it isn't magic. It's just we consistently thought about the rules about how we should do this, and so we've got addition working. Okay, all right. So one more, I guess, and then we're done. Okay, so we're getting bigger here, and so our first number is 101111. And our next number is 101111. Notice that the first number is 1, 2, 3, 4, 5, 6, 7 bits long. And the next number is 1, 2, 3, 4, 5, 6 bits long. And so here's our first number, 7 bits. Okay, that means 7 columns to the number. And our second number is 6 bits, but I put in the leading 0. Okay, and I put the carries in there. All right, but when you first start, of course, you wouldn't see that. You would just see this, okay, without the carries, okay? But let's do it. let's go through that. And so, you might say, well, how big are you going to make these numbers? Well, I could make them big. I wouldn't go crazy. There's no reason to give you a number which is like 32 bits long or anything like that. I mean, maybe 10. Just to make sure that you know how to do this, because it's the same rule for each column. Okay, only the very first column is different because there's no carry in the first column. But as soon as you get to the second and subsequent columns, there could be a carry. Okay, and I say could be a carry. You could say, well, you know what? I'm going to carry the 0. Then there would definitely be a carry. All right, so let's do this. All right, so in the first column, we got 1 plus 0. Okay, 1 plus 0 is 1 with no carry. And then in the second column, we get 0 plus 1 plus 1, which is 0 carry 1. And then we have 1 plus 0 plus 1, which is 0 carry 1. And then we have 1 plus 1 plus 1, which is 1 carry 1. And then we have 1 plus 1 plus 0, which is 0 carry 1. And then we have 1 plus 0 plus 1, which is 0 carry 1. And then we have 1 plus 1 plus 0, which is 0 carry 1. And we're done. Okay, and maybe just one more time, okay, since I'm going through that quickly. And so let's do that. We have 1 plus 0, which is 1 carry 0, okay, and then we have 0 plus 1 plus 1. So it's just like 1 plus 1, which is 0 carry 1. So we now have 1 plus 0 plus 1, which is the same as just 1 plus 1, so that's 0 carry 1. And now we have 3 1s, so we have 1 plus 1 plus 1, which is 1 carry 1. And now we have 1 plus 1 plus 0, which is just the same as 1 plus 1, which is 0 carry 1. 1 plus 0 plus 1 equals 1 plus 1, which is 0 carry 1. And finally, we have 1 plus 1 plus 0, which is 0 carry 1. And we're done. Okay? And I mean, I said a lot of zeros and ones there, but if you go through it on your own, you'll get good at it. Okay. Now let's just check again. This is optional, but since we're doing it together, let's check. So the first number is a 2, okay, and followed by a 1, followed by a 2, no 4s, an 8, a 16, no 32s, and a 64. Okay. So 1, a 2, an 8. And a 16. Whoops, what'd I do? Okay, an 8, and a 16. So there's my 8 and 16. All right, whoops, an 8, 16. No 32s. All right, and then a 64. So if we add 1 plus 2 plus 8 plus 16 plus 64, we get 91. 91. So 101101 is 91 in decimal. The next one is no 1s, a 2, a 4, an 8, no 16s, and a 32. A 2, a 4, an 8, no 16s, and a 32. We add them together and we get 46. Now 91 plus 46, let's just do it. This is decimal. 1 plus 6 is 7. No carry. 9 plus 4 is 13, and there you go. So our answer had better be 137. Well, here's the answer we got. Okay. 10001001. Does that work out to 137? Let's check. So we have a 1. There it is. We have no 2s and no 4s. The next one is an 8. There's the 8. We have no 16s, no 32s, no 64s, and 128. There it is. So 1 plus 8 plus 128, ta-da! That's equal to 137. All right, so I'm going to stop now. If you need more, there will be an additional video, a tutorial video, in which I'll just do one addition after another, as well as multiplications, okay, for practice. But I think as far as we've gone, this is good enough. Okay, let's go on. So you're going to be responsible for addition, binary addition. You're also going to be responsible for binary multiplication. So let's take a look at how binary multiplication works, okay? So for instance, let's say that I ask you to multiply 365 times 52, okay? So what do? Well, the first thing you do is you align the numbers. So there they are, 365. The 5 is in the ones column, the 6 in the tens, and the 3 in the hundreds column. And 52, the 2 in the ones, and the 5 in the tens column. Then what? Well, then you're going to start with the digit that's in the ones column of the second number. So this number that I've got here, that 52, that's my second number. Okay, all right. So now the 2 in the ones column there like that, you start with that one. That's the one you start with. And what do? You're going to multiply this entire top number, 365, by 2. Okay, it's like you ignore the 5 right now. We'll get to the 5 later, but you ignore the 5. And now what you do when you do that is you have to go 2 times 5. Okay, but as soon as you do 2 times 5, what you wind up getting is 10. And you can't write 10 below the line here. So what do? You do the same thing that you did with addition. You write the the digit in the ones column below the line, and the digit in the tens column, you carry it. Okay, so you're doing a carry. So over here, what you do is, in the first column, you do 2 times 5, and you get 1 0. In other words, 10. I should say 10 now, because this is decimal. Okay, so you do 2 times 5, and you get 10. And what do you do with that 10? You write the 0 below the line. There it is. And you carry the 1. There it is. Okay. Now what do? Then you do 2 times 6, and 2 times 6 is 12, and then you add in that 1. Okay, in other words, in the next column, in the tens column, you do 2 times 6 plus 1, which is 13. Okay, so 2 times 6 is 12, plus the 1 that you carried is 13. And what do with that 13? You write the 3 below the line, and you carry the 1. You write the 3 below the line, and you carry the 1. All right, and we're still working on that 2. So what do? You do 2 times 3, and then you add in the 1. So 2 times 3 is 6, plus 1 is 7. And there you go. 2 times 3 is 6, plus 1 is 7. You write the 7 below the line, and there is no carry. And you're done multiplying by the 2. Okay? Basically, so far, all you've done is 365 times 2. Okay? The next thing you're going to do is you're going to add in 365 times 50. Okay? Why 50? Because that 5 is in the tens column. Okay. Now, we don't always think of it as 50, but it is. It's 50 because it's 5 tens. It's a 5 in the tens column. You're going to do the same procedure, but because you're doing it in the tens column, everything below the line gets shifted over starting from the tens column. Okay. So now you're going to do, you can get rid of these carries because that was for the 2's additions. You can now forget the 2 and you move on to the 3. I remember when I used to do this, it really annoyed me because I'd have all these carries and I'd be rubbing off the carries because, those carries were done. They were for the other one, and then you have to start over. It could get pretty messy if we're doing this with pencil, okay? I don't remember what grade I did this in. I probably grade 3-ish or so, grade 4 maybe. I don't know. You probably know better than I do, all right? So, but now we're done with the 2. We got 730. We're going to start with the 5. So you go 5 times 5, okay, and you get 25. So 5 times 5 is 25. You write the 5 below the line, and starting in the tens column, and you carry the 2. So 5 times 5 is 25. You put the 5 down here below the line in the tens column because you're really multiplying by 50. Okay, so you go 5, and then you carry the 2, and there's the 2 that's carried. Okay, now what? Well, now you do 5 times 6. All right, 5 times 6. And that's equal to 30, and then you add in the 2, and that gives you 32. Okay, so you did 5 times 6 plus 2 is 32. You write the 2 below the line, and you carry the 3. Okay, so you write the 2 below the line, and you carry the 3. Finally, you do 5 times 3, and then you add in the 3. So 5 times 3 is 15, plus 3 more is 8. So you go 5 times 3. Whoops. Okay, 5 times 3. Here we go. 5 times 3 plus 3 is 18. And you write the 18 below the line like that. There's no more digits, so you don't have to carry that 1 any further, okay? And now we're done with the multiplication. Now, the only part that we have to worry about is adding those 2 numbers, okay? Now, some people, might have been taught to put a 0 there. That's fine, okay? Some people might have been taught, you just start in the tens column. So when you do 5 times 5, you put the 5 underneath this 5 here from the 25 underneath that 5 because it's in the tens column, whatever, okay? It works out to the same thing. So finally, you've got this addition here, okay? So basically, you're adding the multiplication with the 2 plus the multiplication with the 50, and that should give you the total multiplication. And, you go 0 plus 0, so there's effectively a 0 right there, okay? So 0 plus 0 is 0. That was easy. And then you go 5 plus 3, that's 8. And you go 7 plus 2, that's 9. And 8 plus 8, well, there's effectively a 0 there. So 0 plus 8 is 8. and then another effective 0 there, so 0 plus 1 is 1. Okay, so once you've added the 730 to that 1,825 shifted, so it's actually more like 18,250, okay, shifted, you get your answer, which is 18,980. Okay, so there you go. I say phew here, phew, because there was a lot of work there. Okay, and we're going to examine what that work is, just what we had to do. So you do 365 times 52 and you get your answer. You can bring out your calculator to check that, okay, because most people don't do long multiplication this way anymore. They just do it on their calculator, and so we've kind of become rusty at this. So one of the reasons I did this is just to remind you, that you don't need your calculator to do this, to get your brain going. But you know what? I'm probably most of you remember how to do this and could do it, but you know what? It's annoying, isn't it? And so you just bring out your calculator and you do it on your calculator, because as I said, this hurts the brain. Okay, so it is hard in decimal, but believe it or not, you can make a machine that does this. And like I said, this fella Babbage, here's his name if you want to Google for what he did. Okay, Babbage did do that. He did build a machine which did all sorts of arithmetic and beyond. He actually did, some much higher level mathematics too with gears, but it's very hard to do. Okay, if we were to repeat this in binary, the first thing that we'd have to do, is we'd have to memorize our multiplication table in binary. Okay, because when I did this multiplication here, let's go back to this, I didn't write down the multiplication table. Okay, it's kind of like our addition table, but you'd have to have a multiplication table, because you're going to be doing 2 times 5, and you're going to be doing 2 times 6, you're going to be doing 2 times 3, and then you're going to be doing 5 times 5, and 5 times 6, and 5 times 3, like that. So you have to have this multiplication table. And what does this multiplication table look like? Well, there are 10 possibilities for the first number, there are 10 possibilities for the second number, digit I should say, 10 possibilities for the first digit, 10 possibilities for the second digit, for 100 numbers that you have to memorize in your multiplication tables. Okay, that's a lot of numbers. Now, you don't have to memorize all of them, because 3 times 4 is the same as 4 times 3. Okay, that doesn't quite split it in half. It's not 50, but I think it's like 55 that you have to memorize. Okay, and so yeah, that does reduce it a little bit, but not totally. Okay, and so it turns out that you've got quite a few numbers that you have to memorize. Okay, let's take a look at our multiplication table in binary. There it is. Okay, remember the first digit, there's only 2 possibilities. Either the first digit is a 0 or the second digit is a 1. Okay, and then the other one, the second digit, either that's a 0 or a 1. So you've only got 4 possibilities, and here they are. Okay, that's the first thing that makes multiplication in binary much easier than decimal. The first thing. Let's take a look. Let's go through our multiplication tables. So ready to memorize your multiplication tables? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. Okay. Essentially, that's exactly the same as in decimal. Okay. But it is binary. It is binary. Okay. So the only time you're going to get a 1 is if you have 1, 1. If you have no ones, then you've got nothing. If you have 1, nothing, like 1 times 0, you've got nothing. And if you've got no nothings, you've got nothing. Okay, so there you go. That's our multiplication table. It's trivial. There's something else that's very important about this. It makes life really easy for multiplication in a binary. There is no carry. Okay, so if you did like 2 times 7, you get 14. So why is there a carry in decimal? Well, 2 is 1 digit. 7 is 1 digit, but when you do 2 times 7, you get 14. That's 2 digits. And that second digit, the one in the tens column, has to be carried into the tens column, okay? But take a look here. Every time you have 1 digit for the first number, and you have bit. 1 bit for the first number, 1 bit for the second number, you always get 1 and only 1 bit for your answer. There's never a carry. In addition, there is a carry, because 1 plus 1 is 1, 0, and there's a carry. But in multiplication, there is no carry. Okay, and that makes the multiplication table and long multiplication in binary very, very easy. Okay, I shouldn't say very, very easy, but definitely easy. Okay, and so that's what I said here. So a minute ago I did 2 times 7. It works like say 3 times 7. Okay, 3 is a single digit. Okay, that's your first number, and the 7 is a single digit. But the answer, 3 times 7, is a double digit, okay? And so what you would say here is you would say something like, 3 times 7 is 21, or you'd say 1 carry 2, okay? Because you have to have that carry for the 2 into the next column, all right? So there you go, all right? Let's do some multiplication, and you'll see how this works. So let's multiply 11011 by 101, all right? Now, what you do is you start off by aligning the numbers. There they are, okay? So this one from the first number is aligned with that one from the second number. This one is aligned with that one in the 2's column, and then this 0 is aligned with that one in the 4's column, okay? You see that alignment here. All right, good. Then what? Well, just like in decimal, you start with that bit right there, okay? And you say, I'm going to multiply the entire top number by that bit, okay? Well, essentially, you're multiplying by 1. So what you're going to do is you're going to go 1 times 1 is 1. I have it right here, okay? Here's the first one. So 1 times 1 is 1. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. And 1 times 1 is 1. No carries, okay? And we're ignoring that those other numbers. Remember, we're just concentrating on the this digit right there. Sorry, that bit right there, okay? So that's the bit which is in the 1's column of the second number, okay? This is the second number. This is the bit in the 1's column. That's where we start, okay? But if you're multiplying a number by 1, if you're multiplying that top number by 1, basically multiplying a number by 1 doesn't change it. And so what do you get? Below the line, you get that exact same number all over again, okay? Let me get rid of that wrap there. Top number. Okay, there we go. All right. So notice when you multiply by this bit here, you just get that top number repeated, because essentially you're just multiplying by 1, and multiplying by 1 doesn't change anything. All right. Well, now, since we're done multiplying by this number, what do? We move on to that number. So here we are. We move on to that number. And so now we're going to go 0 times 1 is 0. 0 times 1 is 0. 0 times 0 is 0. 0 times 1 is 0. 0 times 1 is 0. Okay? So we're getting all zeros. And it's in the 2's column, so you have to start over here. But basically, you're going to go 0 times 1 is 0. There it is. And then you go in the 2's column. You start in the 2's column because, let me get rid of that wrap. Okay, so you're in the 2's column, so you go 0 times 1, 0. 0 times 1 is 0. 0 times 0 is 0. 0 times 1 is 0. And 0 times 1 is 0 again. Basically, since you're multiplying that number by 0, you just get 0. Okay, now you still kind of need it for the placeholders, those zeros for the placeholders, so here they are. So, how many bits are in that number? Well, there are 5 bits in that number there, right? 1, 2, 3, 4, 5. Okay, and so down here, you're going to get 5 bits, but all of the bits are going to be 0 because you're multiplying by 0, and they are shifted so that they start in the 2's column. Okay, so again, that 0 times that 1 gives you a 0 in the 2's column below the line. Okay, that 0 times that 1 gives you a 0 in the 4's column, and then 0 times 0, that's that 0 there, and then 0 times 0 is that 0 there, and 0 times 0 is that 0 there. Okay, and I think you see why this is easy, because there's only 2 possibilities. Either you're multiplying that top number by 1, or you're multiplying that top number by 0. Okay, and so when you go to do the multiplication by the third number here, the third bit in the second number, what are you going to get? Well, you're just multiplying that number by 1, and so you just get the top number repeated. And there we go. Okay, there's the full multiplication. Now I still have to add below the line. Okay, but there's the full multiplication. All right, so if you take a look here, when I multiplied by 1, the top number by 1, I got that. Took the top number, multiplied it by 1, I get that. Took the top number, multiplied by 0, and I get that, starting in the 2's column. Took the top number, multiplied it by 1, and I get that, starting in the 4's column right there. Okay, so either you get the number reflected back, either you get the top number reflected back, or you just get a bunch of zeros as placeholders. Okay, and that's it, and that's just repeated for every single bit in the second number. Okay, no carries, nothing like that. All right, Now we're still not done. What do you have to do now? You have to take these numbers and you have to add them. Okay? And so we're going to add these numbers. Now at this point, life can get a little bit complicated because you're going to have as many rows here as you do columns here. As you're going to have as many rows here, 1, 2, 3, as you have bits. Each bit in the second number leads to a row. And above, I only taught you how to add 2 rows. And here, we're actually going to add 3 rows. Okay? And you say, oh, how do I add 3 rows? Well, what you could do is you could add 2 rows at a time and then add in the next one and add in the next one. Okay? So you can always add them in pairs. On a test and in the assignment, I'm not going to make you do a lot of a really big addition. Okay? What I'm going to just have you do is some small the bottom number will have a small number of bits in it. Okay, so you don't have to do you won't have a lot of rows to add. But you know what? Let's try to add these 3 rows and see what happens here. Okay, so over here we have. So I'm just looking at this stuff down here. Okay, because we're done with the multiplication, the first step. Okay, so we got 1 plus 0 plus 0. Okay, so if you got 1 plus 0 plus 0, that's equal to 1. Okay, and then the next one in the 2's column, we get 1 plus 0 plus 0. That's also equal to 1. And then in the 4's column, we get 0 plus 0 plus 1. That's also equal to 1. And now we have something interesting. 1 plus 0 plus 1. That's 0 carry 1. And so this carry now is that carry that's highlighted. That's from the addition in the previous column. And now we have 1 plus 1 plus 0 plus 0, which is the same as 1 plus 1, which is 0 carry 1. And now we have 1 plus nothing plus 1. So that's just 1 plus 1 is 0 carry 1. And that's 1 plus 0 plus 0 plus 1, which is 0 carry 1, like that. And we're done. Okay? And that's it. That's the answer. All right? Now, like I said, you might get into some trouble here if you have 3 rows to add. And take a look. When you get to this point, you might have 1 plus 1. When you did get to this point, we had a situation where we were adding 4 bits. 1 plus 1 plus 0 plus 0. Now, it turns out that adding those 4 bits was the same as just adding 1 plus 1 because 2 of them were 0. But you can get into a situation where you're adding 1 plus 1 plus 1 plus 1. Okay, in other words, you're adding 4 ones. And you're going to say, well, what do I do then? I'll show you in a minute. But for the purposes of tests, we're going to avoid that. Okay, but there's the answer. And now, before I show you that complication that I just mentioned, let's just check by converting to decimal. And so the first number that we were multiplying was 1011, okay? And that's a 1 plus a 2, no 4s, an 8, and a 16. 1 plus 2, no 4s, 8, and 16, which is equal to 27, okay? The bottom number is a 1, no 2s, and a 4, which is 1 plus 4, which is 5. And if you do 27 times 5, that's 135, okay? So this number here had better turn out to be 135. And so let's see. We have a 1, a 2, and a 4. Okay, there's my 1, 2, and 4. There's no 8, no 16, no 32, no 64, and there's a 128. So there's my 128. So again, a 1, 2, 4, and a 128. 1, 2, 4 plus 128 is 135. Exactly what we expected. Okay, so it worked. Okay, and then finally, this is I put note here, but you can almost call it a caveat. That means like a watch out. This could happen. Oh, that made a wrap. Okay, let's get rid of that. Sorry, my text editor tends to wrap on me when I don't want it to. But basically, you'll have as many rows to add as you have bits in your second number. So what do I mean by that? Here, my second number has 3 bits. So when you multiply by all 3 bits, you're going to get 3 rows. Well, what if I had 5 bits in my second numbers? Well, then you'd have 5 rows, and so on. And because carries happen so often in binary, you could easily get into a situation where you have something like 1 plus 1 plus 1 plus 1, okay? You say, well, what's 1 plus 1 plus 1 plus 1? Well, 1 plus 1 is this many fingers, right? 1, 0. And plus another one is this many fingers, 1, 1. But if you have this many fingers, decimal 4, that's 1, 0, 0. So you're in this weird situation. You go, well, how do I carry? How do I carry this? Well, that 0 would be in the column where you're adding. This 0 will be carried over to the next column to the left. And this 1 would be carried 2 columns to the left. Okay? So you could actually have a carry not only into the next column, but 2 columns over. All right. And you say, but that never happens in decimal. It does. It's just that it happens very rarely in decimal. Okay. If your second number in decimal were 11 digits long, you could be in a situation where you're adding 9 11s. Okay. And if you're adding 9 11s, well, no, that's 9 11s is 99. No, you'd have to have 12. Okay. You'd be over 100. And then what would happen is you'd put the one digit in that column, and then you'd have two carries, one into the tens and another one into the hundreds column. Okay, very rare that it happens in decimal, but it can. Okay, so but in binary, because carries happen so often, uh, it can happen. It happens quite often. Okay, nonetheless, I'm just mentioning that because I want to be complete in my description of multiplication. I'm going to try to avoid situations where this happens. Okay, I do expect you to know that it happens, but I'm not going to throw problems at you where you have a lot of this going on. Okay, so that's good enough. Let's do one more multiplication. Just to see how this works. So 111 multiplied by 101. All right. So the first number is 111 and the second number is 101. By the way, first and second number, you can exchange them. There's no reason to here. So my first number is 111. My second number is 101. Okay. And I'm multiplying by 1. Okay. So I just get the number reflected. Okay. Great. That takes care of that one. The second one I'm multiplying by 0, so it's basically all zeros, just as placeholders, but shifted over into the 2's column. And then over here, I multiply by 1, and I get that number again. Okay, so you can see here, I get the number, and then I get the number replaced by zeros, and then I get the number again. Okay, so wherever there's a 1 here, I just get the number reflected back at me. Wherever there's a 0 there, I just get a bunch of 0 placeholders. Okay, and then shifting over to the columns appropriately. Now this time, I hope this doesn't confuse you. I put the carries on the bottom, okay, which you could do. It doesn't matter where you put the carries as long as you know that the carries are there. So you go in the ones column, you go 1 plus nothing, plus nothing, plus nothing like that. Okay, so you got 1 plus 0 is equal to 1, and there's no carry. Okay, and now I'm going to go 1 plus 0 plus 0, okay, is another one. And then I'm going to go 1 plus 0 plus 1 is 0, carry 1. Okay, so I put the carry there. Okay, one more time. 1 plus 0 plus 1 is 0, carry 1. And then I've got 0 plus 1 plus 1, that's 0, carry 1. And then 1 plus 1 is 0, carry 1, and we're done. Okay, and let's check. These are small numbers, so you should have them memorized. 111 is 7, 101 is 5, 7 times 5 is 35. Is this number equal to 35? Let's make sure. So that's a 1, there's a 2, there's no 4, no 8, no 16, and a 32. So a 1, a 2, and a 32 is equal to 35, and ta-da, it works. We'll put some exclamation points in there because I don't know. I wouldn't say it's amazing, but you know it's kind of neat that it just works. Okay, there we go. All right, so I'm sorry, I've got some horrible wrap going on here. Let's try to fix that wrap. There we go. So my next point here is at this point you should realize that binary multiplication is easier than decimal. Okay, and we don't need we don't need that multiplication table, and we don't have to worry about carries. Now, if we were to build a mechanical mind, that is a machine which does this, it'd be much easier to build a machine that doesn't have to worry about carries, that only has like actually 4 possibilities for multiplication, and then does the addition, which would be like another part of the machine that we've already done. We've already done addition. So you'd have a multiplying part, the part that just does, this part, okay, that just does that part. And then you'd have another part of the machine which does the addition, okay? And putting them together, you now have a multiplying machine, okay? And again, because this multiplication here is really easy, no carries, very simple multiplication table, it's much easier to build a machine that does this than does its equivalent in decimal. All right. Okay, so now you're responsible for multiplication. Okay, now let me show you long division. All right, so long division, I'm not going to expect you to do long division, but I want to show you long division because long division is probably the hardest thing that you have to learn to do in arithmetic. Okay, and you can get into situations where there's an awful lot of guessing going on, and Even reasonable people will guess wrong. Okay, even if you know all your tables, you'll guess wrong because some subtle things can happen. Okay, I won't go into all the subtleties. All right, but most people just use their calculator. But if you had to do long divisions by hand, you would every once in a while you'd hit a situation where your guessing doesn't quite work right. Okay, so let's take a look here. We're going to do this long division here. Okay, so what is 18,990 divided by 52? Okay, that's similar to one that we did before, where we did the multiplication of 365 times 52, but there we got the answer 18,980. Here I purposely put 90, okay, because I don't want the two to divide evenly into one another. Okay, I want to show you how the remainder works. Okay, so how does this work? Well, you write it into first this form here like this. Okay, so you write it into that kind of a form where you have the bigger number inside the division symbol, and then you have the 52 outside. Okay, and then you move one decimal over at a time, starting from the left here, and you go, okay, how many times? That's what my little caret here means. Okay, that little caret there just says, well, just go this far, and you ask a very simple question: how many times does 52 evenly divide into 1? And the answer is it doesn't. Because why? Because 1 is smaller than 52, so there's no, you can't get a 52 out of a 1. Okay, and so that 0, usually don't write it in, but I'm going to write it in. It's a placeholder up there. Okay, this basically says 52 divides into 1 0 times. Okay, and then I move my my little placeholder over another one. Okay, and now I ask the question: how many times does 52 divide into 18? Okay, so how many times does 52 divide into 18? Once again, 18 is smaller than 52, so it goes in 0 times. Okay, and so what you do is you put a 0 up here and you move your little mental marker over one more digit to the right. Okay, and now you say, okay, how many times does 52 go into 198? All right, and this is where the guessing begins. Now, most people wouldn't even go through these first preliminary steps. Okay, I just wanted to show you that I'm trying to make an algorithm that a machine would do. You're looking one digit over at a time. Most people would go, oh, I have to start with at least 3 digits there, like that. Maybe they would try 2 and they go, oh, that doesn't work, and they'd start there. Okay, but anyhow, here we go. Here's the first one where the answer is not 0. How many times does 52 go into 189? How do you answer that question? How do you answer that question? So one way is you could do this approximation game. Okay, and the approximation game has a couple of steps. So you say, well, 52 into 189, that's a little bit hard. So how about instead of that, let me just divide both numbers by 10 and then drop the remainder. Okay, so you ask an equivalent, not an equivalent question, a nearly equivalent question. How many times does 5 go into 19? Now, why 19? Well, because this is 189, and I just rounded it up to when I divided by 10, I rounded it up to 19. You might round down to 18, and that's where those subtleties come into place that I'm not going to go into. So you just ask the question, how many times does 5 go into 19? Now, what you could do is basically this is a reverse lookup in that multiplication table. In other words, you look at the answer and you try to figure out from the answers what the question was. In other words, what do I multiply 5 by to get a number which is 19? And the answer is there is no number. You have to find the one which is closest but doesn't go over 19. That's really hard. Okay, that's really hard to do. Not only do you have to have the multiplication tables memorized, but you kind of got to step through them and say, what's the biggest number that I can multiply by 5 and not go over 19? Okay, so, I'm just going to pretend I was guessing. I go, well, 5 times 5. No, 5 times 5 is 25. That's bigger than 19. No good. Well, okay, 4 times 5. Well, 4 times 5 is 20, and that's still over 19, so it can't be 4. What about 3 times 5? 3 times 5 is 15. That's less than 19. There it is. Okay. 2 times 5 also, would be less than 19, but it's not the biggest one, which is still less than 19. Okay. So you got to play this bracketing game, and so you come up with the guess, and it really is a guess of 3 times. All right. And then, okay, you say, okay, well, what's 3 times 52? And you multiply that out and then you subtract. Okay, so here we go. We put a 3 up there. That's our guess. Okay, we could be wrong. I'll show you how you know that if you're wrong. And then you go 3 times 52, and that turns out to be 156. Okay, I'm going to skip the details of the multiplication. All right, but there you go, 156. And because it's in, I guess that's the thousands column, you put the 156 in the thousands column, and you go, okay, I'm going to take 189, I'm going to subtract 156, so 9 minus 6 is 3, 8 minus 5 is 3, and so I get this 33. Now, at this point, we know that we guessed right, and here's why. First, the number is positive, not negative. If it's negative, you went too high. If we had picked 4 there, we would have had a negative number there, and it wouldn't work, okay? So the next reason you know it worked is because that 33 is less than the 52. If by some fluke you guessed wrong, this 33 wouldn't have been 33. It would have been a number bigger than 52. Well, then you have to bump that number up. This is not at all easy, okay? And kids struggle with this when they're learning it in in the lower grades, okay? I don't remember when I did this. I think maybe 4 in grade 5, like we're talking serious amount of mental power before you can start to get this right, okay? I could be wrong about those grades, okay? So don't quote me on them, all right? If you're an education major, you can tell me. All right. Okay. So, all right. Now, the next thing you do is you say, okay, I'm going to get rid of my little mental marker, but basically my mental marker would move to here. Okay. And I would bring down the 9. And now I have, instead of 33, I'm looking at 339. And now I ask the question, how many times does 52 go into 339? How many times does it go in? And again, this is a guess, all right? And the way I would guess is how many times does 5 go into 34? And again, it doesn't. If it were 35, you could say 7, because 7 times 5 is 35, but no, that's too big. So the next one down is 6, and you go, well, 6 times 5 is 30. And you go, I bet you 6 will do it, okay? All right, so you put a 6 there, and you go, okay, 6 times 52 is 312. All right, and now we subtract. So we have 339, we subtract 312. So 9 minus 2 is 7, 3 minus 1 is 2, and we get 27. And again, you know it worked. You know it worked because 27 is less than 52. If that number had been a number bigger than 52, instead of 27, you got, say, 54, well, then you'd have to bump it up by at least 1, okay? All right, so now what? Well, now we're ready for the next number. So you move your little mental marker over, and now you bring down the 0, okay, that last number there. So you have the 27 becomes 270, and now you ask the question, how many times does 52 go into 270? And you guess 5 times, okay? And so you go 5 times 2 is 10, and then 5 times 5 is 25 plus 1 is 26. And there you go. 5 times 52 is 260. 270 minus 260 is 10. And you're done because there are no more numbers to bring down. And the 10 is less than the 52. That 10 is called the remainder. Okay, that's the remainder. Because when you divide two integers, they don't always divide evenly. Okay, so here you have a remainder of 10. Okay, this time I said not only is it hard, but it is a very, very hard. I wouldn't be sure where to start to even make a machine that does this. Okay, and in terms of gear, I could see how in terms of gears you could do the multiplication. Okay, I could see that, but the long division is beyond my ability to imagine gears that could do that. All right, so if you wanted to build a machine that did long division, you'd have to think long and hard about it, the way Babbage did. Okay. And that's in the 1800s, so we're talking a serious amount of sophistication, probably lots of gears and so on. Okay, let's take a look at the equivalent in binary. Remember, the whole purpose for doing this was to just show you, well, first remind you how you do long division, because I know no one does it anymore. You just use your calculator. Remind you how long division is done, and just show you how incredibly hard it is without a computer. Okay, now even building a computer based on this is hard, as I said, with the gears. How about we do it in binary? How about we do this division here? Now, this is a division from above, okay? Well, above we did a multiplication. So I won't go back to it, but if you take a look above, you'll see that I multiplied 101 by a number, and I got that as my answer. So if I divide that by 101, I should get that first number that I had above. All right, so let's do it. So you start off by putting everything under that division sign, the long division sign. Usually you put not usually, you put the numerator inside and you put the denominator outside. Okay, and then you've got that little mental marker there like that, and you go through one digit at a time. Okay, and so now we're just looking at this part of the number so far, and you ask the question, how many times does 101 go into 1? Okay. When you ask that question, how many times does it go in? How many times does it divide in evenly? There's only two possible answers, 0 or 1. Either it divides in or it doesn't divide in. Equivalently, either the number is smaller or it's bigger than the number you're trying to divide in. If the number is smaller, it doesn't divide in. If the number is bigger, it does divide in. So the guesswork kind of disappears because you're just checking whether the number is bigger or smaller. So in this particular case, you say, okay, is 101 smaller than 1? Well, no way. 101 is like 5 in decimal, and 1 is just 1. Is 5 smaller than 1? No. Okay, so 0 times. And again, I put in the 0 there just to as a placeholder. Then you move your little mental marker over. Okay, 101. All right, there you go. And now you ask the question, how many times does 101 go into 10? All right, so we're looking at this mental marker here. All right, and again, 101 is bigger than 10, and so it goes in 0 times. All right, and so we'll put another 0 there, and we'll move our mental marker over. And now we're looking at these 3 digits, and we ask the question, how many times does 101 go into 100? So 101 is like decimal 5, 100 is decimal 4, and is decimal 5 smaller than decimal 4? Is 5 smaller than 4? No. So once again, we get the answer that it goes in 0 times. So once again, we put a 0 there, and we move the marker over. And now we're looking at those 4 digits there like that. And we ask the question again. How many times does 101 go into 1000? Okay? And the answer is once. Why? Because 101 is now smaller than 1000. Okay? So 101, because it's smaller than 1000, goes in 1 time. All right. In decimal, how many times does 5 go into 8? Once. All right. Is 5 smaller than 8? Yes. So it goes in once. That's it. There's only 2 possibilities. Either it goes in or it doesn't. So it goes in. All right. So we're going to put a 1 up here. Right there. We're going to put a 1. Oops. Right there. We're going to put a 1. Okay. So there it is. There's the 1. And now what do? We do 1 times 101. And we get that number. Okay, and we place it, where our mental marker was. In other words, we place it below that number there, 1000, and we align the the columns. All right, now what do we have to do? Now we have to subtract. What do we have to subtract? We have to subtract 1000. We have to subtract from 1000 101. Okay, so 1000 minus 101. I didn't teach you subtraction. Okay, and you're not going to be responsible for subtraction or division, but it's not that bad. Although, just like there's a lot of carries when you do addition in binary, there's a lot of borrowing when you do subtraction. And so the borrowing kind of gets crazy. You have to borrow from multiple columns over. Now that happens in decimal too, where you have like situations where, like, if you're taking 100 and you subtract 99, you have to, like, the 0 in the ones column has to borrow from the 0 in the tens column, but you can't, which then has to borrow from the 1 in the hundreds column. So you might have to go several columns over, but it gets crazy in binary. It's like that, but in steroids, the borrowing. So let me just quickly do for you a subtraction. So let's just concentrate on this part here, that minus that. Okay, so there it is. Okay, and of course you start in the ones column like that, start in the ones column, and you do 0 minus 1. Well, 0 minus 1 is -1, right? If you have nothing and you take 1 away, you've got -1, but we can't work with negatives. And so you say, okay, well, I have a 0 there, what do I do? Well, imagine if this were decimal, you have to borrow from the next one. Okay, so you say, okay, great, I'm going to borrow from that one. But you can't borrow from that one because there's nothing there. So you say, okay, let me go to the next one. I'm going to borrow from this one. Well, wait a sec, there's still nothing there. So you have to borrow from the next one. And so you go to there. Okay. Now, if you borrow from that one, what do you get? Well, if you borrow from that one, you get a 0 in this column. Okay. And you get a 10 in the next column. All right. Because what you did is you took a 2 from a column which was twice as big as the previous column, and you brought that into the lower column, and so that's a factor of 2, and so you get 10 in the fourth column. That 1 in the eighth column is the same as a 10 in this fourth column. Now that's weird. We don't usually write that, but remember, we're borrowing. We're borrowing, okay? And so here we go with that 10 in that column. But we're not done because we have to borrow all the way down to the ones column. We're in the fourth column. So the next thing you say is, let me borrow a 1. Let me borrow 1 from that 10 in the fours column. Well, when you borrow 1, that's like a 10. We subtract 1 from it because you're going to borrow that, and 10 minus 1 is 1. Okay, in decimal, that's like 2 minus 1 is 1. Okay, so binary 10 minus 1 is 1. So you'll have a 1 left in the fours column, and then you'll bring that 1 into the twos column, but it's going to become 10 in the twos column. Okay, so here we go. We borrowed, and that 10 in the fours column became a 1, and then we bring that into the twos column, and that becomes 10 in the twos column like that. Okay, and are we done? No, we have to do it again because we have to borrow and bring it into the zeros column there like that. And so again, we borrow 1 from that, so 10 minus 1 leaves you with 1 in the twos column, and that brings you a 10, a decimal 2 or a binary 10 into the ones column, and so we have this 10 in the ones column here like that. Okay, I know that looks weird. We don't usually write it that way, but there it is, okay, because we did the borrowing. And now we can do 10 minus 1 in the ones column, and 10 minus 1 in the ones column is 1. So 10 minus 1 is, we write a 1 below the line like that. All right, so it might have been a little bit confusing because you're used to borrowing in decimal, but it's the same thing. The thing I think that gets a little bit confusing is that when you borrow, basically you're doing 10 minus 1. You don't get 9 left behind like you would in decimal. You get 1 left behind, okay, because this is binary. So 10 minus 1 in binary is 1. 1 gets left behind in the higher column, and you get 10 in the column to the right. Okay, and you just keep borrowing that way until you get to the end where you need it. And so here we are. We did 10 minus 1 is 1, and now we have 1 minus 0, that's 1. Okay. And then finally we have 1 minus 1 in the last column, in the fourth column, and 1 minus 1 is 0. And in the eighth column, there's nothing to subtract, okay? So basically, once you're finished the subtraction, you get this answer here. So 1, 0, 0, 0 minus 1, 0, 1 is equal to 1, 1. Okay? That's what that subtraction is. Let's check. Well, what is 1, 0, 0, 0 in decimal? That's 8. And what is 101 in decimal? That's 5. So we get that 8 minus 5 is equal to 3, and 1, 1, sure enough, is 3. Okay, so I'm not going to expect you to, do binary subtraction, but there it is. It's not too bad. Okay, I just, the course isn't about this. The course is about getting to that adding machine, and so I want you to see the next step, which is going to be that adding machine, and then eventually how all information gets represented in terms of ones and zeros. Okay, so so here we are. We had this minus that, and when we subtract, we get 1, 1. Okay, and how do we know it worked? That we did it right? Well, is 101 bigger than 1, 1? In other words, is this number here smaller than that? Sure enough, it is. Okay, and so we're ready to bring down the next number. Okay, so I've got some bad rap going on here. There we go. So we're ready to bring down that next number. So there it is. Okay, so now we bring down that number. Okay, and now we ask, does 101 go into 110? And the answer is yes. 101 is 5, 110 is 6. Okay, does 5 divide into 6? Yes, it does, one time. Okay, and so over here we'll put a 1 up here. Okay, like that. And 1 times 101 is, of course, 101. And 110 minus 101, all right, think about it, that's 5. That's like 6 minus 5, that's just 1. And there's the answer. Okay, and I didn't even bother with the borrowing, but if you wanted to see how the borrowing would work, 0 minus 1, you can't do it, so you'd have to borrow that 1 there, leaving a 0 behind, and then you'd have 10 minus 1 is 1, and that 0 minus 0 would be 0, and that 1 minus 1 would be 1. Okay, a 0 there because you borrowed that 1 into the other column. Okay, so there you go. 110 minus 101 is 1, and so we're left. And did it work? Did we put the right number up here? The answer is yes, because that number is bigger than that number. Okay, or conversely, this number is smaller than that number. Okay, great. Let's bring down the next one. There it is. And now you ask, how many times does oh, I've got wrapping going on again. There we go. So how many times does 101 go into 11? And the answer is 0 times. 101 goes 0 times into 11 because 101 is bigger than 11. Okay, so since that number is bigger than that number, it doesn't go in, so we're going to put a 0 right up here. Okay, right there. We're going to put a 0 there because that number does not divide into that number. Okay, and so there we go. There's that 0. And now bring down the next digit. I should say bit. Okay, there it is. All right. And, oh, I'm sorry, guys. I got some bad wrap going on here. Let me do this. There we go. That reads a little bit better. Okay, so we brought down that 1, and now you ask the question, how many times does 101 go into 111? Well, 101 is smaller than 111. Okay, there it is. And so it goes in 1 time. Okay, basically that's 5, decimal 5, and that's decimal 7. So is 5 less than 7? Sure enough it is. And so we are going to put a 1 right there. Okay, so there's that 1. 1 times 101 is, oh, I scrolled too far. So 1 times 101 is 101. And so now we have 111 minus 101. 1 minus 1 is 0. 1 minus 0 is 1. And we get that it is equal to 10. All right, the subtraction here, 111 minus 101 is 10. That's 7. That's 5. 7 minus 5 is 2 in decimal. Okay, did it work? Yes. 10 is smaller than 101. 2, decimal 2 is smaller than 5. All right, so it worked. All right, and then finally we bring down that last digit. There it is. And now you ask the question, how many times does 101 divide into 101? And the answer is exactly once, because after all, they're the exact same numbers. Okay, so how many times does 101 go into 101? Once. So we're going to put a 1 right here. Oops, right there. Okay, there's that 1. Then we do 1 times 101 is equal to 101. And 101 minus 101 is equal to 0. Okay, ta-da. And let me just quickly fix the wrap there. And if you take a look above, that's exactly what we found above. Okay, so we had this as our answer. There's our answer. Where did you get that? There's the answer right there. And now I won't scroll back up, but above what I did was I did an example for multiplication where I took 11011 and I multiplied it by 101, and I got this number here. What I did here with the long division is I inverted that. Okay, and so you could see here that the long division is easier because all you're doing at each point here is you're saying, does this divide into that? Nope. Does this divide into that? Nope. Does this divide into that? Nope. Does this divide into that? Yes, and there's only one possibility, 1. So subtract that, and we got this. Okay, and you bring down the next number. Does this divide into that? Yes. Subtract, and we got that. And then you ask, and then you bring down the next number like that. You ask, does this divide into that? No. Bring down the next number. Sorry, I scrolled a bit too far. Where's that? Does this now divide into that? Yes, once. Okay, multiply that by that. Subtract, and we get that. And then we bring down that number again. And we go, does this divide into that? And the answer is yes, once. So either it's not dividing in or it is dividing in. And you just keep going through that. There's none of this guesswork like how many times does it divide in. It either does or it doesn't. And how do you decide if it does or it doesn't? Well, is it bigger or is it smaller? Since this is bigger than that, it does divide in. Since this here, okay, before we brought down the rest of it, before we did this, when we were at this point, we said, does this divide into that? The answer is no, because it's smaller. And so by just doing that over and over and over again, oh, I wish I hadn't done that. Okay, there I fixed it. Okay, because this does not divide into that, we added 0. Then we brought down the next one. We said, well, does this divide into that? And the answer is yes. Okay, so the guesswork is just reduced to a very simple check of whether it's bigger or not, whether this number is bigger or smaller than that number. Okay, and if it is, you put a 1. If it isn't, you put a 0, and you just move on that way. All right, you can almost see how you would build a machine to do that. Okay, in fact, I can see how to build a machine to do that. All right, for binary. And so suddenly a problem which was horrible to make into a mechanical mind long division becomes much easier in binary. Okay. All right, so we're at the end of the lecture. Let me just say very quickly what I did here. I showed you how to add in binary. Okay, I showed you how to multiply in binary, and those you're responsible for. I also showed you how long division works in binary. You're not responsible for that, but what you are responsible for is understanding that the division in long division in binary is much easier than long division in decimal, and that makes it much easier to build a mechanical mind that does long division in binary than in decimal. Okay, thank you. Bye bye.